In this module, we'll discuss basic sensors and the principles, mainly physical principles, under which they operate. So some of the sensors that we will talk about are specific to biomedical instrumentation. Others are just generic and can be used in a number of applications. So I'll try to point out when the terminology that we use is specific to biomedical instrumentation as opposed to when it's just a general term. So, a couple of terms. A transducer is basically a device that converts energy from one form to another. So, for example, if you're measuring sound and converting it to an electrical signal, that would be a transducer. A sensor converts a physical parameter to an electrical output, and an actuator converts an electrical signal to a physical output. Now, the first kind of measurement that we want to talk about are measurements of displacement. So, in this particular textbook, the author categorizes or characterizes sensors and transducers by what you're actually measuring. So, the first category of measurement will be that of displacement. Basically, these sensors measure the size and movements of organs, tissues, etc. So, one example might be trying to measure the variation of the size of the heart chamber or the volume of the heart chamber. In this lecture, we'll talk about three electrical type measurements of displacement: resistive, inductive, and capacitive. And then we'll look very briefly at piezoelectric as well. So first, thinking about the resistive displacement sensor. Basically, these are a function of the resistance of the sensor. And as a displacement occurs, a wire or a connection is going to move along a resistive wire or coil, making the change in resistance proportional to the displacement. So here are three examples of different kinds of potentiometric devices for measuring displacement. The first one, figure A, we're actually looking at translation. So this arrow V naught is moving up and down, and the output voltage is proportional to the resistance from the sliding contact to the negative contact. So as this slides up and down, the amount of resistance involved, it's basically creating a voltage divider. And so the amount of resistance at the divider output is changing, and it's directly proportional to the displacement or to the distance x. So the change in resistance is proportional to the change in x. The single turn is a way to measure rotation. So you have a rotating contact in this case, and the rotating contact rotates around a resistor that's set up in an arc. And obviously, as you rotate through some angle phi, you're changing, once again, you have a voltage divider set up, so you're changing actually the output voltage. This is a little misleading. This is actually a hard connection between the contact on the potentiometer and the positive terminal of V naught. It's not an open conductor, so it's just something in the drawing that maybe could be a little confusing. If you need different kind of sensitivity, you can make a helical coil, and that can also measure then actually both linear displacement as well as angular displacement. So you actually could do two different kinds of measurements with the same sensor. And I want to point out at this point, and I'll try to make this point multiple times, that while we're showing these with like traditional electric circuits elements, most of these now are fabricated on either on a chip, or they're fabricated, using just on circuit board fabrication techniques. So you don't really see like giant potentiometers used in this application. But these are just showing the circuit diagram of how it actually works. And strain gauges are probably one of the most common measurements for making very small measurements. And one of the issues with biomedical instrumentation is that often the movement or the changes are small. And so you're trying to make measurements on very small distances. So if you're trying to move very small distances across a resistive element, then you're going to have very small changes in the resistance. So what happens with a strain gauge is that as a material is stretched, as long as it's stretched within the elastic limit, the resistance of the material changes. And because the change in resistance is going to be very small, basically we take the strain gauges, which are effectively acting as resistors, and we put them into a circuit known as a Wheatstone bridge. And a Wheatstone bridge is actually a circuit that's capable of detecting very small changes in resistance. So here is a circuit diagram of, in this case, in figure A, we have a strain gauge pressure sensor. It's got a little diaphragm here. It's clearly measuring like a liquid pressure. So you can see the diaphragm is able to move back and forth, and as it moves back and forth, it's applying strain to this to these strain gauge wires. So they're actually changing their physical geometry, which is changing the resistance. The figure B illustrates the Wheatstone bridge setup, um, where Rx and Ry are calibrating resistors. And so what you do is you set up Rx and Ry under equilibrium conditions where you don't get any output voltage. And then if one of the resistors in the bridge, which would be R1, R2, R3, and R4, if one of those changes slightly, then you pick up a change in voltage. That's measured right here. And so you can pick that up even if it's very, very small. So here are some equations that describe the strain gauge. Basically, the resistance of a wire is rho L over A. And then you have to look at what is going to change. So we're going to make the assumption that the area is not going to change much. That basically what's going to change is the length because you are stretching it. And then we also can make an assumption that the actual resistivity of the material is going to change because that changes with um, with strain. And then we can also build into this the fact that as you stretch a wire, it makes some sense that as the length increases, the surface area will probably decrease. And so what happens is we take the differential of R, which is the change in resistance, and then basically take the derivative, the partials with respect to all three variables. So the first term is the change in resistance proportional to the change in length. The second term is the change in resistance proportional to the change in area, and the third term is the change in resistance proportional to resistivity. If you then do some algebraic manipulation and you let your d's go to deltas because they're actually finite changes that we can measure, and we're making the assumption here when we let a differential dr go to delta r, we're making the assumption that we're operating within a linear range. So everything is linearly related, which is mostly true, maybe not quite true on the area, but close enough. So you basically then get that delta R over R, which is the unitless change in resistance over resistance, is proportional to delta L over L, inversely proportional to delta A over A, and proportional to delta rho over rho. Now we get the, we can further sort of do some variable changes by incorporating what's known as Poisson's ratio. That relates the change in the diameter delta D to the change in length. So for a wire, delta D over D is proportional to delta L over L, and inversely, and the proportionality constant is minus mu. Sorry, it's directly proportional, it's just a negative constant. So when we substitute this relationship into that center term, we can get rid of the area term by making, once again, some algebraic changes because area is related to diameter of a wire. And so when we do that, we get two terms, one that's proportional to delta L over L and one that's proportional to delta rho over rho. So the delta L over L is a dimensional effect, and mu is a property of the material related to its mechanical properties. Delta L over L is the actual physical change in length over length. Delta rho, or the strain, delta rho over rho is the change in resistivity over the resistivity, and it's referred to as the piezoresistive effect. When you have a metal strain gauge, the dimensional effect is the dominant effect because the resistivity of a metal is not incredibly sensitive to strain. When you have a semiconductor, the piezoresistive effect is the dominant effect because the semiconductor is highly sensitive to strain, and so its resistance will change more with the fact that it's under strain than the geometric issue. So in order to just compare different kinds of strain gauge materials, we use a gauge factor, G, and that's just kind of done in the industry to compare materials. Basically, the change in output voltage is given by equation 2.6, but the gauge factor is delta R over R divided by delta L over L. And so you see this term, which is a property of the material, and then you see this term, which is a property of the piezoresistive changes as well as the changes in length. So the change in the output voltage can be written as delta R over R naught times the change in the input voltage. So these are just some figures of some typical strain gauge units. These are referred to as bonded units because in this case the gauge is actually bonded to a backing, and so the backing moves and then that makes the wire move. And there are 3 different examples here of different geometries that are commonly used. You want your geometry to be, your geometry is sensitive to the direction in which you expect the strain. So if you're expecting stress in this direction to create strain here, notice that you've got the length of the wire oriented in that direction. And notice that it kind of doubles around itself. This means that instead of one little delta L, you've actually got 4 of them because you've got 4 lengths of the wire that are being pulled. So that gives you a little more sensitivity in your measurements as opposed to just having one wire that came out there. Here are some properties of some strain gauge materials. You can see the gauge factor varies widely. We have some metals. You probably recognize nickel, iron, chromium, copper. Copper is 2.1. This combination of metals is 2.1. Common strain gauge combination. Notice that silicon, you're here at 100 to 170, for N-type minus 100 to minus 140. Also notice the temperature coefficient of resistivity. The silicon is extremely sensitive to temperature. So going with a silicon device, you gain that you have a great sensitivity in the gauge factor, but you also now are going to have some impact of temperature. This is just an example of a measurement that's being made of remote pressure. This one being made in the human leg. This is an example of a strain gauge output. So figure C here is the bridge output measuring arterial pulse in the same region. So another type of displacement sensor is the inductive displacement sensor. This measures displacement by a change in inductance. The inductance is a function, in general, inductance is a function of the number of turns in a coil, a geometry-based factor, and the magnetic permeability of the coil core. So a coil can certainly have an air core, but a magnetic core adds sensitivity to the measurement because it makes you more likely to manipulate the inductance. The inductance of a coil is N squared Gu, where G is the geometric factor, mu is the magnetic permeability, N is the number of turns. So first of all, you can see from figure A and B, you have different coils, and you are varying the amount of overlap between the coils, which means that you're varying the flux coupling, which means that you're varying the mutual inductance, which means you're varying the inductance in the circuit. Figure A has no mutual inductance. You're varying some self-inductance here. Figure B, you are working with the mutual inductance in both of these figures. Figure C, you actually now have a core, and so because this core is what's moving, it's changing how the coils in the circuit couple. So basically you're manipulating typically the inductive coupling or the geometry of the inductor in order to induce a change and measure a displacement. So the LVDT is a linear variable differential transformer. It's used a lot to measure pressure, displacement, and force. It has a primary coil and two secondary coils that are connected in series. The coupling between the two coils is changed because you have this very high mu slug that is allowed to move up and down, and the two secondary coils are connected in the opposite direction. The reason for that is so that you can get a wider range of linearity. So you put a sinusoidal voltage on the primary coil, and that then causes it to couple to the secondary coils. The coupling is going to depend on the positioning of this um, core material. And so as the coupling changes, the output voltage will change. If this core is in the middle of the two secondary coils, then the voltages are equal and the output signal is 0. So the problem with the LVDT is, if you look at this figure, here's our displacement. At this point, when the output voltage is 0, we have moved to a 0 place of displacement, so we're right in the center. At this point, there's some ambiguity because you now don't know, do you turn around and go the other direction, or are you continuing to go the same direction? So in order to do that, you actually have to look at the phase of the voltage so that you know, did you move all the way through, or did you go to the middle and then turn around and go back, as is illustrated in this position. So you have to have a phase sensitive detector that tells you to be able to unravel that. Are you going with a positive angle, or are you going with a negative phase angle? Capacitive sensors would be the final sort of circuit element type of measure of displacement. So capacitance, as we know, is a function of the dielectric properties of the material, the spacing between the plates, and the plate area. And the change in capacitance is a function of displacement. You basically are changing the spacing between the plates. You could do a sliding kind of thing where you slide one plate back and forth, and in that case you would be changing the area. But in this particular example, we actually have a change in X, the spacing between the plates. Obviously, capacitance is proportional to the constant epsilon naught, and then the relative permittivity of the material, the area of the plates, and the spacing between the plates. So the capacitive microphone is a classic example of an RC circuit that monitors sound vibrations above certain frequencies. So you basically have a capacitor here. The force on the capacitor plates is going to change the spacing in between them. As you change the spacing in between them, you're changing the capacitance. You're coupling that with a resistor in the circuit, and so basically this is acting like a high-pass filter, meaning if your frequencies are high, you will get an output voltage. If your frequencies are low, you will not get an output voltage because all the voltage drop will be across the capacitor. So because the current voltage relationship for the capacitor is a differential equation, when you calculate the output voltage, you basically get a function of frequency and a time constant. So you have the applied voltage, E, you have x sub 0, your spacing, and then you have j omega tau over j omega tau plus 1. So this is how your voltage to displacement function looks, where tau is a constant. That's a function of the resistance, the capacitance, and basically the resistance and the capacitance. It's RC. So you can make that a function of x sub 0 here. So you can see that as your x sub 0 gets very small, that your time constant would get very large, and as your x sub 0 gets very large, your time constant would get very small. So the last thing to talk about in this section is the piezoelectric sensor. This works off a slightly different effect. Basically, you're basing this on the piezoelectric effect. And that is that the mechanical strain on the material induces a voltage by distorting the dipole charges within a crystal lattice. So you've got, in most crystalline materials, you have a crystal lattice, and often the atomic structure within that lattice minimizes its energy state by aligning its dipole charges. When you apply strain or stress to that material, it basically moves those dipole charges within the lattice, and that then creates a voltage. So if K is a constant proportional to the called the piezoelectric constant, and Q is charge and F is force, then the output charge is this K times the force, so it's proportional to the force. So because in a capacitor, voltage is actually directly proportional to charge, not current, then you can substitute the induced charge due to the piezoelectric effect for Q in the voltage to charge relationship. So normally we would have voltage as Q over C. Substituting KF here, we now have voltage that's proportional to a force. And then if we, substitute our formula for capacitance, we can see that the voltage is proportional to the force and the displacement x. So here's an example, an equivalent circuit of a piezoelectric sensor. So here's your crystal, and basically your delta x is going to occur in this direction, so your force is applied vertically. You have a couple of plates here to the crystal, and then they come back with a voltage on them into an amplifier. The way to model that is that you have a charge generator here, which is basically your change in X, and then you have some resistance that is like a sensor leakage resistance. It's basically the resistance of the crystal. You have a sensor capacitance, C sub S. You have a cable capacitance, and you have an amplifier input capacitance. So this looks like a parallel RC circuit, and you can basically then take your charge generator and replace that with a current source that's proportional to dx dt. So if you're measuring voltage, which is proportional to current in this circuit, or related to current in this circuit, then you're actually going to get the velocity, and you'll then have to integrate that in order to get the displacement if you're measuring displacement. So piezoelectric is a good way to measure velocity directly.